It's my pleasure to welcome Erdal Aydin. He is a scientific employee at the Max Planck Institute for Dynamics of Complex Technical Systems. During his PhD, Erdal is supervised by Kai Sundemacher and Professor Dominic Bonvin from EPFL. He holds a bachelor's diploma in chemical engineering from METU and a master's diploma in chemical and biological engineering from Koch University. His research interests are in the areas of nonlinear dynamic optimization, model-based control, process optimization, real-time optimization, and numerical methods. And so with that, we'll go ahead and turn the time over to Erdal Aydin. He's going to be giving the talk today on tailored indirect algorithms for efficient online optimization.
Dan, thanks again, John, for the kind introduction and this invitation. So today I'll be talking about how can we tailor indirect algorithms to be convergent and efficient for online optimization. So I will focus basically on batch and semi-batch processes, but these methods are also can be applicable in principle to continuous processes. So as you mentioned, my supervisors are Professor Kai Sundemacher from Max Planck Institute and Professor Dominic Bonvin from EPFL. And I would like to particularly acknowledge Jens Bremer from Max Planck Institute and Diogo Rodriguez from EPFL for the fruitful discussions during this project. All right, so here's the outline. I will basically start with the semi-batch process operation schemes and characteristics. Then I will move on with the dynamic optimization approaches available in the literature. Then I will introduce you the tailor-made efficient algorithms that we are proposing. And finally, I will finish the presentation by giving some online optimization case studies. Okay, let's start with the semi-batch operation. So let's assume an elementary reaction where A and B goes to C. We would like to operate semi-batch wise. So we start with some of the raw materials in the reactor when time is equal to 0. Then we basically feed some of the raw materials inside the reactor. So this can be one-phase, two-phase, or multi-phase system. We basically employ the process. And at the end of the day, after the final time of the process, we get the product C after maybe some downstreaming, or if you're lucky enough, just at the end of the batch time. So typical examples are pharmaceutical industries or some biopharma applications. Car driving is also can be considered also a semi-batch process as well as cooking. And nowadays our microchips, microindustry works quite with semi-batch processes. So what are the characteristics of these processes? Well, they have quite transient behavior and strong nonlinearities. In addition, they don't have any steady state, which puts a question mark for classical PID algorithms. We have tight product quality limits to be able to sell these products. And one of the problems is that our flexibility reduces with time as the batch goes on. So if you have any problem in the beginning of the batch, and since also we have irreversible behavior at the end, if you're making a mistake, we usually end up with losing the batch. And we have quite uncertainty. In our model equations and limited measurements. So in the literature, shrinking horizon NMPC is prescribed as a solution technique for these or tackle these issues. So the idea is basically to do dynamic optimization always until the end of the batch time and kind of update our optimal inputs at each sampling instance until the final time. But it's basically doing successive dynamic optimization and doing some estimation or measurement until we reach the final time. So let me elaborate this with a small simulation case. So let's say that at the first time instant, we do our dynamic optimization. This is our input, and this is the state that we're trying to maximize at the end of the batch time. The batch time is 70 time units. So this is the first optimal profile, and let's say that we implement the first input as we do in MPC studies. So What we're basically doing is always dynamic optimization until the final time and implement the first input. But as you can see, the previously computed optimal inputs are not optimal anymore on the real-time instance. So that's why we need to solve this dynamic optimization problem always until the batch time and cope with the flexibility reduction and try to optimize our objective function at the end of the day. Okay, so this was a brief introduction to semi-batch processes. Now the question is, how can we solve the dynamic optimization problems related with nonlinear model predictive control? So we basically have a cost function in our dynamic optimization problems, which can always be formulated until the final time of the state values. We have equality path constraints, usually as given as ODEs for semi-batch processes, with pre-given initial conditions. In addition to that, we have some path constraints, inequality path constraints, to be satisfied at each time instance, as well as some terminal constraints, which should be only satisfied at the end of the batch time. So, numerical solution methods related with dynamic optimization problems can be divided into two topics. One is the direct methods, and the other one is the indirect methods given by Pontryagin minimum principle. So the direct methods are usually called as first discretize, then optimize, whereas in indirect methods, we basically optimize the problem first and then discretize to get the solution, to get the optimal solution. So in direct methods, we can also talk about two main branches, which are sequential and simultaneous methods. In sequential methods, we basically discretize our inputs, but integrate our state equations to get the optimal solution. Well, basically, we're solving the we're doing integration until we reach the optimal point. But since we're trying to also make our path constraints feasible, this method can sometimes be considered as expensive for inequality path constraints. In terms of simultaneous methods, we both discretize our inputs and state equations. Well, this is usually there is a trade-off between approximation and optimization while we're going to the optimal solution, but simultaneous methods are known to be usually efficient for large-scale problems. There's also a method called multiple shooting, which behaves as a hybrid between these two methods, but today I'm not going to be, I will not talk in detail about multiple shooting. Okay, if we talk about the indirect methods given by Pontryagin minimum principle, we can talk about shooting-based and gradient-based methods. So we know that shooting-based methods usually requires good initial guesses, and in the literature they're considered as being slow and non-convergent, especially for path constraint problems. In gradient methods, we usually do not require that much good initial guess, but these methods are also known as convergence, known as behaving convergence problems for path constraint convergent problems for path constraint problems, and they also usually turn out to be slow in the literature. So today I will propose a convergent-based method which is tailored to be efficient for path constraint problems, basically. Okay, now a few words about shrinking horizon and MPC again. Well, we know that in shrinking horizon and MPC, we always need to employ the dynamic optimization until the end of the batch time. If we use direct optimization methods to do that, we know that we need to employ expensive matrix factorizations that comes to the problem due to large prediction horizons and control horizons, or large input discretization levels, which means large prediction horizon lengths. So, and we also know that due to these matrix factorizations, usually the computational complexity increases as the cube of the time horizon. Now, if we would talk about a direct interior point methods, interior point simultaneous methods, this is the linearized KKT matrix that we need to solve. So the last rho can be eliminated and solved explicitly during the iteration, which brings about this symmetric linearized KKT matrix. Well, usually the optimization methods available in the literature can be tailored can be exploited to be efficient, like using their sparsity, by using some special linear algebra, or by employing some cyclic reduction, especially from the group of Professor Behaviour and Professor Zawala. This is like a hot topic right now. And there are also some works which proposes some sensitivity-based update for these methods, some advanced step or real-time tailoring algorithms from the group of Professor Moore Steele. These are kind of other ways of dealing with this matrix factorization costs. But today I will talk about an alternative way using indirect methods to deal with this computational complexity. Basically, we know that if we can tailor these indirect methods, we can get the computational complexity increase as the linear of the time horizon. Professor Mark Cannon from Oxford have already published some papers which are talking about this, basically for input constraint linear systems. But we will extend this method to be convergent for path constraints, nonlinear dynamic optimization problems. So yeah, and we hope that we can get the real-time computation faster than commercially available methods. Okay, so this was basically about dynamic optimization. Now let's move on to tailor-made indirect methods that I was talking about. So Pontryagin was the person who proposed Pontryagin minimum principle. So this was basically the extension of Euler-Lagrange equations. The interesting thing with Pontryagin is that he lost his eyesight at the age of 11 due to oven explosion at his home, but he was able to finish the school, became one of the most well-known mathematicians in the 20th century, and his mother was the one who was reading books to him when he was studying. So the basic idea of Pontryagin minimum principle is to reformulate the direct optimization problem into an indirect. So we can see that the objective function should be replaced by something called as Hamiltonian, which includes our system equations, our path constraints with some multipliers included and with the co-state values. So by definition, we know the dynamics of these co-state variables, and we know actually the final time of these co-state variables. This is given with the PMP conditions. And we also have some slackness conditions to be satisfied of the optimal solution, as well as we have the stationary condition, which means that the sensitivity of the Hamiltonian with respect to inputs should be 0 at any local optimum point. So please recall that I mentioned the indirect methods can be non-convergent for path constraint problems. The reason is actually these Lagrange multipliers. You can see that we know the dynamics of other multipliers, but we have no clue about mu values. And if we try to update them at each iteration by using some shooting method, this can be costly. And at the end of the day, we may not even reach to an optimal solution. We may not converge. So we basically propose a 3-step tailoring algorithm to cope with this issue. The first step, let's say that we're not that much interested in the exact value of mu. We just choose a penalty value or tune a penalty value to ensure feasibility as a barrier type, as a version of barrier type, instead of parameterizing and shooting for this value. And let's say that we use some logic conditions. Let's say that if you're inside the feasible region, we set this value as 0 to satisfy this KKT condition. Or else, if we are outside the feasible region, if our iterate is infeasible, we just tune a penalty value to be used for this, as well as for the terminal constraints. Secondly, we propose indirect adjoining to be used for pure state path constraints. By pure state path constraints, I mean the path constraint is only dependent on the state values. So we basically take the time derivation of this until we get the explicit inputs inside this. and then replace the indirectly adjoint path constraints with the original path constraint. So we know that this value should be 0 at the KKT, and its also derivative should be equal to 0. Let me illustrate that with a case. So let's say that we have a tank. We're basically dosing some water, let's say, inside it. And we have the path constraint of the volume should be less than or equal to 1.1 liter. So our original constraint is V minus 1.1, less than or equal to 0. We take the time derivative, and we have V dot less than or equal to 0. Basically, we are reducing the index of this path constraint. And since we know that V dot is equal to U, we put U inside the equation, and then, here. So we will use this U instead of the original path constraint to make the iteration feasible. How we do it? We say, if the iteration is infeasible in terms of the original path constraint, compute the U, which makes it 0. So basically, we enforce active constraint, or we employ some method which is active path constraint seeking. So let me go back our tank example. Our original constraint is this U. So if the volume is higher than or equal to 0 or equal to 1.1 liter, we basically set U equal to 0, which makes sense, right? After this point, we don't dose, and we keep this feasible. So one last illustration about this. This is our original path constraint and the original problem. We reformulate it by using indirect adjoining like that. And then, at some infeasible iteration, we basically put the iteration to be active on this path constraint. Well, we will see that for semi-batch problems, this kind of will work, because usually semi-batch problems are, the optimal solution of semi-batch problems are designated with active path constraints. I will be talking about this in a bit. Okay, so by doing this three-step tailoring, we reformulate the original indirect problem, and we use logic decisions to activate the mu values. To activate the path constraints. That's why we can eliminate the mu values from the problem. And we basically integrate for lambda dot, the Erdal multipliers, and the state equations. And at the end of the day, we are projecting the gradients related with the indirect methods. And we can solve the original problem as an unconstrained optimization problem by using some quasi-Newton algorithm at the end of the day. So basically, we just need to update the input values in this iteration scheme. Okay, now let me move on with our first case study taken from this paper in the literature. We have a fat batch reactor. Our aim is to optimize the amount of C at the end of the batch, which is half an hour. D is the product that we don't want. So we have some input constraints for this dosing. We have temperature limits on the batch reactor. Semi-batch reactor. We have a volume constraint that we just talked about, and we have some heat removal constraint, which is basically 1.10 to the minus 5 joules per hour. We shouldn't reach this value during the operation. All right. So we solved this problem by the proposed PMP-based method, and we took the analytical solution number 2 from this paper published in Computational Chemical Engineering 2 years ago. So if you use this if you solve this problem by these two methods, we can see that we don't get the exact optimal values, but we get the exact sequence of the optimal inputs. So both dosing and temperature behaves the same in terms of solution arcs, and at the end of the day, we get very similar optimal solutions. So we basically kind of approximate the optimal solutions here, but since we have very similar cost values, we can say that it is catching the optimal behavior in some sense. We also solved this using a direct simultaneous method by using IPOpt and comparing with the analytical solution number 3. We say that both also proposes a different sequence, a different input sequence than the analytical solution 2 and PMP, but at the end we also get very similar optimal objective values. So we can say that we get different local solutions with both methods, with all methods actually, different far-fight type solutions. but we can get nearly the same optimal costs with considerably different input profiles. Well, we saw that, but what about the computational time? If we compare the computational time with the direct simultaneous and PMP-based methods, we can see that when the discretization level is getting higher, our computational cost increase is not that much considerable with the indirect method, with the PMP-based method, whereas with the direct one, the computational cost is increasing a little bit faster. And the thing is, like, we need to solve these matrix factorizations for larger input discretizations. This expands our matrices, and factorizing them are getting a bit more expensive than the indirect one. In indirect one, we basically attach to integration, and we know that integration is efficient for higher input discretization, whereas these matrix factorizations are getting problematic as the horizon increases. Okay, now let me move on with the second problem. So this is like a hydroformylation process. This is the reaction scheme and reactor depicted in this picture. Our aim is to optimize the value of 3-decanol after the batch time. So this is a two-phase system. Therefore, we have some gas-liquid mass transfer equations. Our inputs are also constrained this way, and we shouldn't reach the upper bound of total partial pressure of 20 bars inside the vapor system. So we also solve this problem by using the PMP method and the direct simultaneous method by using 500 discretization levels. These are the optimal inputs proposed by two different methods, and this is the objective value, and this is the path constraint that I was talking about. So again, in this case, we see that we're getting very close optimal solutions at the end of the batch time. They both behave as the same 3-arc solution structure, and we get nearly the same optimal cost with these two methods. If we again happen to compare the computational times with the direct simultaneous and PMP-based methods, we see again that for the increasing input discretization level, PMP-based method turns out to be much faster than the direct simultaneous one. And therefore, we say that if we interplay the state and cost states and eliminate the Lagrange multipliers from the optimization problem, we can get a bit more efficient for large time horizons. But I need to again mention that this is an approximation, and since we are more interested in the online optimization cases, we basically stick with the speed of this indirect method, with having very close approximated optimal cost values. All right. So this was basically the indirect algorithm, the first one that we proposed. Now let's move on with the online optimization case studies. So let's again go back to the hydroformylation case. Now we assume a parametric uncertainty on the rate constants of the problem, as well as the gas mass transfer coefficients, plus minus 20%. And we also assume an uncertainty on our catalyst activity. And we try to solve this problem by using the nominal optimal input we got. So by not taking the effect of uncertainty into account. Now, if we apply this, we see that our path constraint, our pressure constraint cannot be satisfied, and we have a desired product level of. So we have a loss of 15% desired product as opposed to the nominal case. That's why we say that employing some online optimization by using shrinking horizon and MPC can be more efficient in terms of production. And we do that to deal with the effect of the uncertainty on the path constraint. We basically employ some time-varying backoffs. These backoffs can be computed by doing some Monte Carlo simulations. They are kind of computationally complex, but I need to mention that we can do it offline before starting the online optimization. We assume a 15-second sampling time, and we also introduce 5 seconds of measurement delay, which is more close to the reality with practical operations. We use a linear observer, and we introduce some white noise into our measurements. So if we do that, we again see that we can get different input profiles in closed loop, but the optimal value at the end of the batch is still very close. So both values are very close to each other, and we can satisfy our path constraints during the operation. If you consider the sampling, if you consider the computational time of these methods, we see that the proposed PMP method is much faster than the direct simultaneous one. Here, I need to mention that we use warm start to get the solutions, which means we start the iteration with the pre-known optimal values, and at each time instant of the shrinking horizon NMPC, we compute the perturbed solution. And at the end of the day, we see that with the direct simultaneous one, we contribute to 10% feedback delay, whereas with the PMP method, our feedback is only 1%. So here we can say two things. First of all, in real operations, this feedback delay can affect the optimal cost in a bit of negative way. And with this PMP, we can decrease the sampling time, which means we can employ a fast NMPC scheme. By doing this, we increase the optimization frequency, and at the end of the day, we may get even better, close to optimal cost, because we're kind of increasing our capability to do optimization. So then afterwards, we solved this PMP-based controller for 40 different batches, which means 40 different uncertainty realizations. So if we employ a product maximization, we see that the desired product level can be increased by 10% overall in mean, as opposed to the nominal case. We can also employ a batch time minimization problem, which basically gives the set point of the original problem to the controller, and with this way we can decrease the batch time by 20%, 25% as opposed to nominal case. All right. Now this was fully parameterized PMP-based method, but we can also suggest a further tailoring method to be applied to this indirect method, which is called as parsimonious parameterization. So in dynamic optimization problems of semi-batch processes, we see that an input solution arc can be either on a lower or upper bound of an input, which is like Umin or Umax. It can be on a path constraint, which activates actually this path constraint. And in this case, we can compute this value by system equations. Or it can be inside the feasible region, and we call these kind of inputs as sensitivity seeking arc. So these four are the only possibilities for the optimal solution. We can categorize our optimal solutions by using these arcs. I also did that when I was talking about the case studies with the tailor-made indirect methods. So we know that these sensitivity-seeking input arcs usually hard to compute accurately because their contribution inside the sensitivity equations is quite low. And they also negligibly affect our optimal cost. So we're paying a lot of attention to compute the fine shapes, but at the end of the day, we're not getting that much improvement in our optimal cost. But we can kind of propose a parsimonious parameterization method by using the priorly computed solution and kind of parameterize these sensitivity seeking inputs in a different way, in a less computational complex way, instead of discretizing the inputs only using piecewise constant or piecewise continuous values. So let me illustrate this idea a bit further. Let's assume that we have a 3-arc optimal solution, which is Umax, followed by the sensitivity seeking arc, and then Umin. If we write our standardly parameterized indirect method, we need to satisfy these equations. But if we find a different map, an alternative map, by kind of parameterizing the sensitivity seeking input, we can also write the indirect problem in a different way and solve it. And here, let's say, in the previous case, we were having 500 decision variables because we were using 500 input discretization levels. Whereas here, you will see that we only have 3 decision variables. And then the idea is, after this mapping, we employ the same indirect solution strategy that we proposed and solve the optimal solution and see if we get close approximation. Now, let me introduce the case study of a batch binary distillation column. So here we basically have, it's a toy example actually, we basically have three stages. We assume total condenser here. So we have the dynamic system equations, pre-given initial conditions. Our target is to optimize the distilled content at the end of the batch. So here the value here. We have the input constraints. Actually, we have only one decision variable. This is internal reflux ratio, and this is also constraint between 0 and 1. And at the end of the day, if you want to solve this product, we need to have the terminal purity levels of minimum value of 80% of the desired product here, and in the bottoms we shouldn't have more than 20% of the desired product. So, first of all, we use the fully parameterized solution with 500 input discretization levels, and we solve the problem by using a direct simultaneous method. This is the optimal solution. So here, we can see that our optimal sequence of inputs are three archetype, starting with the maximum allowable level, then following a sensitivity seeking arc, and finishing off with the minimum value. And we get something like 40.35 kilomole at the end of the batch time. And our distillate composition purity levels, or the bottom composition purity levels, are satisfied. Okay, now let's assume a constant relation between this, a constant relation of the sensitivity seeking input, and we introduce some switching times. So here we can see that the solution switches at this and at this instant. So instead of the whole parameterized solution, we can map our input vector by only three decision variables here. And let's solve this problem. Now, if we do that, we see that this sensitivity seeking arc can be approximated by this constant value, and at the end of the day, we can get very close optimal solution as opposed to the fully parameterized direct simultaneous method. And we see that these are the optimal inputs of our input levels. So only three decision variables to approximate the global solution. Actually, here it's the global solution, and we only use three decision variables to approximate. Further, we can also assume a linear sensitivity seeking arc for the sensitivity seeking arc. This way, we introduce actually again two switching times and 1 and 2 different values which characterize the beginning and the end of the sensitivity seeking input. And we basically use this linear relation to compute the other values during the optimization iteration. So if we solve this problem, we see that we can even improve the optimal cost in terms of the desired product. And only by introducing one more decision variable, we can have only 0.15% of optimality gap as opposed to the fully parameterized solution. Now let's see if we can apply this to a shrinking horizon in MPC. Because we know that instead of 500 decision variables, we only have 3 in this case. And we know that this is a less complex optimal dynamic optimization problem. And at the end, we have less computational load, or we can end up with faster solutions in this case. Okay, now for this batch distillation problem, we assume a plus minus 10% uncertainty on the relative volatility. And this is the closed solution actually. So we basically employ the shrinking horizon in MPC by using the standard direct simultaneous method and the parsimoniously parameterized indirect based shrinking horizon in MPC. And we see that we're still able to catch the close behavior very close in terms of the distillate value instead of the desired product. So there's only 1.5 minute difference here. And we also see that we satisfy both our terminal purity constraints at the end of the batch. Now, if we compare the computational time we need here, we see that the parsimonious shrinking horizon NMPC requires much less, especially in the beginning of the batch, when this time horizon is the largest, and when we need to employ these matrix factorization levels. This parsimonious shrinking horizon NMPC requires much less time. Then when the horizon shrinks, when we are going to the end of the batch time, we see that they're coming head to head. And after some time, maybe even the standard shrinking horizon NMPC can have faster performance. But recall that we also have flexibility reduction in the beginning of the batch. So we should be we should have an efficient algorithm to solve this online optimization problem, especially at the beginning of the batch, where we have the much flexibility and less computational requirements. All right, so to conclude this talk, I can say that an alternative PMP-based quasi-Newton algorithm can be proposed to be used for online optimization problems, especially for batch and semi-batch processes. Further, we can tailor this indirect method by combining it with a parsimonious parameterization scheme, by using the priorly computed optimal input profiles to reduce the real-time computational load. And we can have two advantages with that. First, we can increase our optimization frequency, and secondly, we have less feedback delay, which may even affect the optimal cost in a better way. So it can increase our optimal cost, especially in industrial applications. And we can say that this is also a promising alternative for limited battery life applications. For example, Internet of Things are quite hot topic. Is a quite hot topic nowadays. And for these branches, we always need we usually need fast and efficient optimization structures. But there are also some open points or some questions that we need to ask. For example, if we have large-scale process applications, integration might require quite a lot of time than semi-batch processes, right? Maybe we can employ some discretization on the system equations and Lagrange multipliers. But even in this case, we cannot be sure that we get proper approximations for our closed loop. So we need to actually investigate this indirect-based methods for large-scale problems. In addition, maybe they can even be much more efficient for smaller-scale problems, for example, wireless networks or robotics, where we actually need to compute the optimal inputs in a faster way, because usually there might be some heat transfer limitations with our CPU. So usually the CPU that we're using for these kind of processes are small, and if you're employing a lot of computation on that, we have heating problems. And to cool these kind of CPUs is a big problem. So usually we need to use expensive coolants to get along with the heat transfer limitations. Lastly, I can also say that we can use these indirect methods for stochastic NMPC for semi-batch processes. Please recall that the shrinking horizon NMPC that I was using was more kind of a robust NMPC. We were using some backoffs on the path constraints, but stochastic NMPC usually results in even better optimal closed-loop optimal costs. Closed-loop optimal values. So it can also be efficient for real-time applications. In addition, it can also be efficient for moving horizon estimation. So moving horizon estimation is a dual of MPC. In MHE, we basically solve the dual problem, the inverse problem. Instead of looking inside the future, we're basically looking inside the we're looking back to the time. So we're looking at the past to compute the values of the states at the time instant that we are in. Basically, at the time instant that we are doing the dynamic optimization. So these can be combined, but so we can say that it's basically, it's typically a new approach, an alternative approach. And I feel that going deeper a bit in mathematics and trying to tailor our methods by using the indirect base, the PMP conditions, we may get up with some improvement in our optimization methods. So some acknowledgements here. Basically, I would like to deeply acknowledge all my colleagues at Max Planck Institute for all fruitful discussions. I would like to acknowledge Professor Dominique Beaumont from EPFL and Diogo again for their contribution. And I would like to acknowledge the International Max Planck Research School for Advanced Methods in Process and Systems Engineering for the funding. And I would like to mention that this is a DFG project funded by German government. So basically, that's all from my side. I would like to thank you for your kind attention on this webinar, and I would like to thank again to John for giving me this opportunity, and I hope that you enjoyed the talk. Thank you.
Well, thank you very much. That was a great presentation and really motivating results in terms of challenging some of the the prior conceptions about how some of those methods are slow or non-convergent. You've done a great job showing many case studies and this alternative method. So we're going to open up this for any questions that the audience may have, and you're welcome to put those in the chat window, or also unmute your microphone if you'd like to just ask a question directly. So we'll go ahead and just give a moment just for those who would like to ask a question. Okay, and also if you'd like to ask a question too, you can also send it to me privately in the chat window, or you can put it to everyone. Okay, so here's one question. You mentioned having active path constraints, seeking. This is an active path constraint seeking method. What if there aren't any constraints for the problems, for the manipulative variables? Does this method still is it still computationally as efficient as you showed?
Well, actually, this is a great question. So we can have some flexibility problems on the inputs. And in this way, we need to include some restoration phase, or we may need to reformulate the problem again in a different way. So maybe we need to include some other bonds to increase the flexibility. Basically, we didn't face it with our case studies, but I would say that you would require a bit more attention in these cases. But I would like to also mention that this may also be a problem with direct methods. So usually, if this happens, yeah, we need to go a bit deeper on the problem.
Okay, great. Hey, another one you mentioned, excellent scaling with some of the time horizons, compared to the direct methods. What about the model size? I noticed one of the examples you showed there was a 3-stage, separation column. What if you had, 30 stages? The model size increased. Do you have any feel for how this method compares to the direct method for increasing numbers of differential or algebraic equations?
So thanks a lot for this question. Well, basically, we know that this kind of parameterization works well if you have less values of inputs than the model equations. So basically, if you have a large model, we can still get some trade-off for these sensitivity-seeking inputs. But if you have a lot of input variables, then it might be a bit hard to tailor this way. So we can basically solve the nominal solution, even if we have 40, 50 state values, and then we can find and we can tailor the input. So basically, this is nothing new. So I'm sorry. So this has been done kind of before for different applications, not for shrinking horizon and MPC, and not with indirect methods. But what they found out is also that for less number of input variables, this works a bit more efficient than the other case. So there were also some papers from the group of Professor Beaumont on this
Great. Okay. In terms of implementing this approach, are there any plans to incorporate this within like a modeling language, or are most of the applications, do they require custom methods for each model?
So if I understand it correctly, you're mentioning about expanding it to be used for other problems by other people, or so kind of extending as a toolbox or so?
Yeah, like if it were like a MATLAB toolbox, or is it possible to do that, or is there a lot of custom work that needs to be done with each application if you change, equations?
I see. So basically, what you need to do is symbolic differentiation in the beginning. I'm talking about this fully parameterized PMP this way. And after the symbolic differentiation, what you need is only an integrator, because you basically integrate your state equations and co-state equations and update the inputs by using some steepest descent, even quasi-Newton method. And so for this parsimonious parameterization case, you can implement it by using a commercial software. So in one of our papers, which is under review right now, we're also showing how we can compute the time sensitivities, the switching time sensitivities. And after reformulating the original ODE functions by using these switching times, you can basically use a commercial software in this case.
Great. And okay, so one last question. Your presentation gave me a lot of, really, it really is motivating. One other thing I'm just wondering about is, there's been a lot of interest recently in mixed integer and, non-continuous variables. What are some of your thoughts on perhaps including mixed integer variables, decision variables with this approach? Do you think it's going to work, or are there fundamental limitations of the method for mixed integer, binary integer values?
Yeah. So actually, yeah, we thought about this, but never applied this. So basically, the fact that we can approximate our nominal solutions by using this method, for example, for branching and bound, this might be useful. But so if you have a lot of changes in these if you have a lot of integer decisions, maybe this can be useful. But this also really depends on the problem type. I can say if you have one or two integer decision, we can combine it even with PMP and employ it for some mixed integer dynamic optimization. But for me, actually, right now, frankly speaking, it's really hard to comment really deeply on that. But I think it would be a good idea at least to try. So thanks for this question.
Okay. And sorry again for the construction noise in the background here. Well, this has been a really good presentation. Thank you for the very engaging, discussion and the motivating results that you have. You're doing great work, and we look forward to seeing additional publications. Sounds like your group has been very productive in terms of getting the results out as well. So thank you for sharing the latest advancements and also these latest results, and we really appreciate your presentation.
Thanks a lot, John, for the invitation, and it's been a pleasure for me to give this talk. I'm also a fan of APMonitor. My former colleague Hassan was the one who introduced this to me, and I'm very happy to be contributing in both CAST and APMonitor.
Great, fantastic. Well, thanks everybody for joining, and we'll go ahead and sign off now.